All right, welcome to the last session of this meeting. My name is Julia Kemper. I'm very pleased and grateful to the organizer, so to Shirley and the organizers, for allowing me to attend. I'm not a cosmologist at all. In fact, I work in data science. So it's a particular pleasure to get to know a new community. And I was just discussing with some of us what your community is, how it is perhaps different from what else I've seen. So, I know very little. I've only been attending since yesterday evening. I see a certain predilection for animal names, camels, tigers, I don't know. So, and I guess a certain love for the Lord of the Rings, I observed. So, but I can say, but it's a pleasure to actually, I enjoyed this meeting very much, and I've seen a glimpse of the problems you are tackling. So Vanessa and I prepared a few slides to give you to get you into the mood to talk about interpretability. And I will speak about the neutral part, the non-physics part, and then Vanessa will take it to the more specific physics and cosmology part. So why do we want to interpret? This is a little cartoon that people often show in this context. This is your machine learning system. Yes, I pour data into this big pile of linear algebra and then collect the answers on the other side. And what if the answers are wrong? Then we just stir a little bit more, right, until it fits. So this is a bit of a cynical view, perhaps, of machine learning. But it's clear that there is a certain need to understand what we are doing, at least if we want to do it well. So what do we want to do? Explain or interpret? So I believe this discourse already goes on in the field for the last, I would say the papers date back to 2015, 2016 that tried to put interpretability on some sort of theoretical footing. So people distinguish between, interpretable and explainable. Interpretable means why did the model just do what it did? And explainable is more like how does this model work? I mean, I guess this is just a little bit of wordplay, but what is interpretability? It's basically like beauty. It's a bit in the eyes of the beholders. So interpretability is a system is interpretable when the operations can be understood by a human. So you see the beholder is there, the human or the scientist, either through introspection or through a produced explanation, right? So that's what kind of the running definition of interpretability is. And why, and what's the problem what are the problems people usually are facing where interpretability could help? Machine learning systems are now used not only in cosmology, as you probably know, but in all kinds of other real life applications. People care about safety, so they would like to understand why their Tesla has just crashed into the whatever, into a police car. So safety, biases, of course, and amplification of biases. You must have heard of this topic. Adversarial examples. You probably also know that machine learning systems tend to be extremely non-robust in ways that the human would never be, right? So there's a tiny perturbation of an image and it suddenly from temple goes to ostrich. How can that be? How can we explain the model that does such a thing? Legal issues, especially the European Union, again, has what's called the right of explanation. So when an algorithm decides you go to prison, you are allowed to find out why that's the case. And that's the GDPR and the laws around it. Other reasons are, you don't want to, the machine learning system makes mistakes. You don't want to repeat them. So it would be good to get some interactive feedback and would be good to understand what's going on. Recourse also, automated kind of test grading, for instance. If you find out how it works, you can game the system. I don't know if that's good or bad, but this is one useful thing. Trust in the system. You want to understand the extreme cases, the rare cases, especially when we talk about bias, the mistakes and whether they're similar to the ones a human would make. And also, how would you change the model if things go wrong? So all these problems can be attempted, at least with trying to interpret the system and to explain it. How does it look like? Well, we all have some sort of notion of what is actually interpretable. So our favorite linear regression is something that people usually consider highly interpretable, right? You have the beta 0, beta 1, and epsilon, and you can kind of slope, whatever, intercept noise. Decision trees are usually considered interpretable. And there we already get into slippery slope territory, because here is a decision tree. You might still think it's kind of interpretable, right? You kind of go along, you know what features distinguish kind of what breaks the answers. But is this interpretable, right? That's all, you know, there's an issue with complexity here, right? So it's still a decision tree, but look at it, right? So is that interpretable? Yes, no. Is it too complex? I'm just putting this up for discussion. How do we interpret? What do we interpret, right? So there is the global versus the local. What does that mean? Do we the local? Sorry, I guess I mixed them up. So do we explain individual predictions, or do we explain the entire model, right? So this is important, and there are various ways, various methods to interpret that fall into one bucket or the other. I'll mention them in a second. Inherent or post hoc. So inherent is usually when you build this into the model, this interpretability. So there's something called rationals, for instance, of course, linear regression trees. If the model is a black box, then we try to be happy with just understanding it afterwards with external methods. And there, for instance, again, heat maps that look at what in the image or what in the data has prompted this response is something that is kind of post hoc. Model-based versus agnostic, again, is it something that would explain this one model, or does this explain or interpret every model? So there are various approaches. I'm just really giving you the keywords here. I won't explain that more. Various techniques that would then work for every model, like LIME, for instance, where you locally try to build a linear classifier kind of into this thing. But this is just, again, to set the stage. So how do people interpret? One way, for instance, is to create what's called heat maps on saliency maps, depending on, I mean, you look at what in the input has prompted the output. And there's millions of methods. You look at the gradient, you look at, leave one out analysis, these type of things, and you create and you find what it is in the image, say, that has prompted the model to, classify it one way or the other. Or for text analysis, which words were the crucial ones that helped in whatever summarizing the text the way it was. So here, for instance, for diabetic retinopathy, they were quite pleased that the model actually looked at the same thing, the lesions that also the surgeon would look at. Saliency maps. So this is just to give you an idea how many gradient-based methods there are, and there are probably many more. To check what is it in the image that the thing actually looks at to figure out that it's a bird or cord. There's another way where a way to kind of understand what models do is to give prototypes. So give examples that, these are dogs. This is the thing that the model would call dogs, right? And then also, I mean, the recent trends, also criticism. What criticisms are the thing that the model can't do. So, this is what the model can do, the top row or in this, the left side, and criticism is what the model can't do, right? So kind of that you understand better what it does. Rationalizing, so that's basically you extract the piece of the data that prompts the answer. So there's sophisticated techniques that work with an extractor and then a decoder to figure out what in the image it is that calls the thing frog. And again, this is something that you can do with the models. All right. So to finish this off, my piece is that this interpretability is kind of in a pre-paradigmatic state, in the sense that there is really no consistent definition of that notion of interpretability that people all agree on. And the cynical view would be that it's what makes you feel good about your model in the end. That's what it is. It really depends on the target audience. And in this case, in this audience, I think it's the scientists that should decide what it is that they care about when they want to make a model, which of these many techniques they actually want to apply, what do they care about? And in particular, one should think what matters in cosmology. And with this, I'll pass it on to Melissa.
How do I change slide here? Oh, the green button, okay. All right, so turning now to cosmology. So I feel like interpretation and interpretability has already been kind of like a recurring theme in this workshop. It has kind of been there with us from the beginning. And so I think also we've already heard a lot in talks. We've had a lot of references to different methods that can be considered interpretable. So I thought instead of going through these again, what I would do is more of a population analysis. So yesterday I went on the arXiv, and I just got all of the papers from AstroPH that had machine learning in it, and looked at the timeline. And even I was expecting it to be exponential, but I wasn't expecting it to be that extreme. But yeah, we've seen, as you can expect, we've had an exponential increase in publications on AstroPH that mention machine learning. Yet when you go into these publications and you look at how many of those actually mention any of these words that kind of refer to interpretability in them, then we are down to only 47. So we only have a 5% rate of publications that actually mention interpretability. And then I was initially planning to do like a big topic analysis on this, but then with 47 papers, there's only so much you can do. So just looked into what, the kind of models that they're using. So I just looked for which of these papers mentioned what kind of methods in the abstract. And it's kind of striking that a lot of them actually mention ICA. And then there's obviously trees and forests, which you just heard are interpretable, neural networks. And then a lot of the more modern or newer methods like flows and variation autoencoders don't really appear yet. And then I overplotted, and then I asked, is this special, or is this different when I looked at the entire population of 1,000 papers? And turns out that it's actually basically the same. So there's not much signal in here. When you look at what kind of other concepts are mentioned, I think one thing that stands a little bit out is that there's a lot of classification going on, not so much regression in the interpretability section, and what deep neural networks are concerned, I think that's a long way to go to have more deep learning papers that also mention interpretability. So I think with this kind of like population analysis, the big question is how can we close the gap between the blue line and the orange line? And also, just to start this discussion, how much do we need to close this gap? This is where we finally come to the discussion part with some questions. So questions for the audience are, what interpretable methods do we have? I mean, we already heard a little bit about this, but maybe we want to, maybe get a little bit of a summary. What are they useful for? What do we think? And Julia already alluded to this. What do we think as cosmologists qualifies as interpretability? So, is choice of features enough? Sensitivity analysis. We heard about built-in physical symmetries. Then, what are the most promising interpretable machine learning methods? Are there any challenges? And then I think very important, what level of interpretability is needed for what kind of applications? Like, do we need interpretability for enhancing simulations? Do we need interpretability for modeling for bill distributions, for LFI, for example? Do we need interpretability for identifying summary statistics? And I guess the least controversial point, extracting physics. So with this, we hand it over to the audience. Any first comments?
So I think I would say like the big difference between like a lot of these methods and astrophysics is a lot of these methods are built for problems where we don't have like a true model that we can interpret, whereas in astrophysics we do have a lot of like handwritten codes to kind of solve these problems, and the machine learning kind of augments that. So I would say like I definitely think that I think we as a community can do a lot more in interpreting models because we do have this level that we can kind of build off of. And yeah, I would say like I'm obviously heavily biased, but I really like symbolic models because that is the language of astrophysics, and that's something that other fields don't really have. They don't have these symbolic models that we can kind of go back to and build insights from.
I was actually wondering about to what extent maybe this community is potentially actually already a little bit conservative about these things and doesn't go all crazy, but just doesn't mention the word interpretability. It just like might be a natural thing to, always try to stick closer to something that you know, because or models that you know or believe because you're venturing into like a place that you otherwise can't like really get a hold of. And in general, I was wondering about the causality in, or like the likely causes for the lack of the word interpretability there. You know, you could think, oh, maybe reviewers don't like that word and they reject all the papers, or the thing like that people tend to want to be as much as possible interpretable, and it goes without saying, or maybe it's a whole new field and it'll be used a lot in the next year. The word will crop up a lot. I don't know.
Yeah, I guess I want to take a little bit of a step back, and I'm not as involved with the astro community, but kind of question a little bit how much of physics being interpretable is us having kind of good opinions of it. For example, you know, there are some mathematical issues, say how interpretable is a three-body problem. We understand equations to some context, but we cannot predict what would happen at a long time scale. Similarly to, you know, in some contexts, we might have some understanding of what a machine learning model does, but we cannot predict everything. Another question, for example, even if you have symbolic equations, say the Einstein field equations, how much do we understand them truly? It might take 20 years of research to be able to come with a reasonable description of a charged black hole, which stem from the Einstein field equations. You know, just because we can write down some simple-looking equations that rely on a huge amount of math does not necessarily mean that we understand exactly what the model is doing. And I think looking at what we require to be happy with our current, you know, knowledge is a good way to inform what we would require from machine learning models to be happy with them also.
Link in some ways between interpretability and extrapolation, extendability. That if you're, you know, and this goes, you know, to the one of the advantages of things like having functional representations of what's going on, or being able to say like this information is coming from the power spectrum plus other information that looks like higher moments and lets us know when we, you know, when we can extrapolate. And in interpretability, to what extent does it matter? What is the link between extrapolation and interpretability?
I think still, it seems to me the word interpretability is still largely related to the fact that whether you have a whole language system or reasoning system behind it, and kind of why we think physics is a typical subject with a logic interpretability is because we have the mathematical language behind it. So I think this also highly related to what David said about extrapolation, right? If you acknowledge, believe in the formula, then you can really extrapolate very boldly. So yeah, so and also you can use your reasoning to really go beyond what you just observe. I think this is also similar to what Pangahei said. Like doing science is not just collecting fact. It's using the blocks to build a building. The blocks themselves are not a building, are not a house. So science is like we should not only just collect some facts, but also organize them, provide some understanding, and the system, the whole system, to talk about it and to reason about it. I think that's actually what machine learning now is kind of lacking. I don't believe in the future it will still be like this. I believe there will be also more research about how to understand kind of the mathematics of a neural network. But at least for now, I think that's still something very missing.
So also just, you know, add to this. So there is, I think, this point to be made, or this question to be asked, like, do we really want, you know, can we always achieve interpretability at the level of where we get equations and, you know, we get some intuition for these equations, like in symbolic regression? Or are we maybe in some cases also okay if we can just verify, you know, if we can, as we, you know, we saw that example with the adversarial attacks, yeah, we can actually by sensitivity analysis, we can look at what kind of transformations to the data would make our model fail. Are we okay with just, running a lot of these tests and then feeling comfortable, like we maybe do, when we run simulations? Usually, there are hyperparameters there that you have to tune, like resolution parameters and so on. And we also, we just like test them, and then at some point we say, now we are confident enough, and we just move forward. Do we feel comfortable enough to do that in machine learning, or do we feel different about machine learning, and why?
I think that for machine learning, or for anything really, right, in terms of science, we have several levels, right? So the first level is trial and error, right? So that's basically what you talked about right now. Okay, so we try things, and if they're successful, yay. If they're not successful, even better, right? And then on top of that, we have reproducibility, right? Okay, so now we kind of suspect that it behaves like that. Let's reproduce it. I don't think that as physicists, I may be alone in this. I don't know. It's a matter maybe of taste. I'm not content with being able to reproduce or just try and error or whatever. I want to know. Right? I'm not okay with. I'm a religious guy, right? I'm not okay with God, reproducing everything. No, I want to know. I want to understand. And so for me, the gateway to understanding is really those equations, right? So unless I think, right, unless we reach some point of these structures, these machine learning spitting out equations, and even that's not enough, right? Then really that's not. It's an okay tool, but it's not what it's all hyped up to be, right? I want first off the equations, and then after the equations, I need to go somewhere, alone, I don't know, and try to understand what these equations actually mean, right? That's I feel is the end game. I'm not sure that machine learning or neural networks can get us there.
There's this paper from 2014 that in the title, it explicitly states machine learning is the high interest credit card of technical debt. And I think that still rings true today. Like every time you build a deep neural network, you're incurring technical debt, and eventually you have to pay it off. And I think that's especially true in science. Like as you build a very deep model, and you don't kind of understand what it's actually doing, you are kind of incurring this technical debt. And this is like the main difference between engineering and science. In engineering, maybe you just want to predict something or do something better. But in science, it's really about understanding why something is. And that's why I think like interpretability should be a core part of ML for astrophysics and physics.
But should it be a core of all of these, like all of our applications, or only for certain applications? Like, what is your take on, for example, modeling probability distributions? Is that the same thing, or enhancing simulation?
I think at some level, like if it's a low dimensional probability distribution, like if it's just like a Gaussian mixture model, like I don't think you need to understand why the Gaussian mixture model has certain parameters. Like I think it's definitely a gradient for when you need interpretability, but I think like in very high dimensional spaces, I think it's very important in the field to have like a strong interpretation of your model, because that's really the point of natural science.
We run HMC, and there's no way, like we can only, in an engineering kind of way, make, test if it has converged and so on. We still don't know. We never know if we actually got the distribution perfectly sampled. So we already use a lot of methods that are like this, right?
Yeah, I don't know. I think it's definitely a gradient, and like at some level we do need, like in the natural sciences, it's just like that's the core of the field, is kind of like understanding why something is. And And especially like if you're modeling physics with this, like sure, if it's like MCMC sampling, that's something where I can see you don't need to interpret what the sampler's doing.
And I was thinking, in simulations, we have a lot of hyperparameters we tune. In modeling, like probability distributions, like HMC stuff, we also have parameters we tune, and like we don't about those. But some is statistics, or maybe like symmetry, extracting physics, then we want understanding. But do we expect ML to give us understanding? I feel like interpretability is one thing. It gives an equation, but understanding is the next step. Like, is it within ML's reach? I don't know. I back to play devil's advocate in this case.
Goals of simple models. So to go to the HMC or MCMC example, I could do a pretty good job interpreting what comes out of my MC Markov chain by evolving a Fisher matrix, right? Getting at the best fit point. And that's pretty close to what the Markov chain gives usually. And you usually learn that there's some degeneracy direction. You actually can interpret. And I'm thinking about work that people do in like climate modeling, which are these really complex models that they don't quite know how to fully interpret, or weather models. And the approach that's turned out to be very valuable is to construct simpler versions, low dimensional versions of that, 1D model atmosphere models, understand that and use that to interpret. And is that valuable to think about in the machine learning context? And I know that there's been, use trees, you use simpler things that yield similar, if not quite good enough results to interpret what the more complex model is telling you.
Yeah, I want to reflect this a bit on just, even if we forget machine learning, this notion of understanding and what do we mean by understanding. So obviously here in the physics community, we're quite close to what we believe is a true description, although no one here would say that we need to understand QFT to understand star formation, even though some of the aspects of nuclear reactions do require understanding of the quantum mechanics in principle. But we have good enough approximate models that we feel describe, that fitted post hoc to observations rather than derived from principles, but describe close enough, the mechanics that we feel happy with those. But if we go like, maybe in chemistry even already, chemistry is not physics extended, right? It's not an application of physics. Chemistry is its own scientific field, and the understanding of chemistry comes from internal chemical frameworks, which we know describes approximations of the reality, which is the quantum mechanics behind it. And then biology is not applied chemistry in that, even though in principle biology could be described by the chemical reactions that happen in our cells, we have no way of kind of building this thing up to that degree, and we have to cheat in the middle, and we introduce other frameworks that help us understand what's happening here. I think my worry is even in something like astrophysics, even though maybe the underlying laws, gravity and so on, are very simple, the emergent phenomena that happen may be so complex that a human just cannot understand it directly through equations. In the same way that, for example, you might say, okay, we have Navier-Stokes for fluids, but turbulence, can we understand it from Navier-Stokes? It's a very difficult argument to make, in my opinion.
I want to address what David and said. Basically, I think that we feel we understand something when it converges on one of two classes that belong in computer science or mathematics. So one of them is regular languages, right? When you have basically a complete dictionary and the rules that go on with that, that in that way we understand something. Or you have a general dynamic that you can, given one step, can predict the next step, but in a let's say justifiable way, right? So in that sense, I think it might be. So this is quite adjacent to game theory, and I think we might look as a community, we might look to game theory concepts in order to kind of borrow those concepts of interpretability in terms of physics and so on.
Also, as a response to David's question, actually, I think the scattering transform developed by applied mathematicians are kind of some toy model of convolutional neural net. Kind of, we know convolutional neural net is composed of the convolution, hierarchical convolution, and the training part, optimization part. So the scattering transform kind of separating them and only explore kind of the mathematical properties of the hierarchical convolution. And then with some simple application, and actually it turns out for lots of physical fields, it worked quite well. We kind of find that what's the role of the convolution, hierarchical convolution, and really we can then ask a question whether we need the optimization part or when we will need the optimization part. Yeah, and I think this is really very interesting and valuable. But this is also something kind of a high risk, high gain research, right? It will be very easy to just apply some machine learning tool in the market now to some astronomical problem and get some good looking results. But it will, in general, be hard to kind of explain why that works well or how what's the limit of it.
I have a more basic question in that, have we as a community ever like discussed what are the levels of interpretability that we have before we decide what level of interpretability is needed for what application? So like, what are we interested in? Is it like just interpolations, extrapolations, predictions, or like understanding some fundamental laws? So yeah, that was the one question that I had, that have people given thought about that? And secondly, regarding like physical equations, my hesitation there is sometimes like, even if you can write down a simple looking equation, I'm not entirely sure if I understand things. Like if I have an equation saying that like the radius of the halo depends on like delta to the power 1.5 plus concentration plus something, I'm not entirely sure if I understand where that delta to the power 1.5 is coming from. If I can use that for predictions, I can use that to construct models, to do inference and everything. But I wouldn't necessarily equate like what Wenda was saying, that writing a simple looking equation with understanding something in that sense. So I don't know if that's what I would call as being successful at interpretability. So yeah, mostly I was wanted to say level of interpretability, like what are the different levels that we are discussing here, to put it in a more concrete context.
Have a vague comment on what Chirag just said, but I think we're conflating maybe interpretability and other stuff. Like I think you get an equation, the point is like to make you to ask the question like why this equation works. And then you have to think about it, and I think that's your job, not machine learning job. But I mean, we're doing our best. but I think maybe you're right, and it's not interpretability, and we're conflating concepts. But I don't know what's the other word then.
So just to follow up on that, there's a difference between like a fundamental relation and like having a fitting equation. So at what point do you know that what you're getting out of the machine learning, if I write down a relation, is it an actual relation that like nature respects, or is it just a fitting formula that turns out to be working? Because if it's a fitting formula, then I can spend my lifetime trying to understand it, but there might be nothing there to understand. So you need to make that distinction as well at some point.
An interesting example, right, is think about the history of quantum mechanics, and the Planck distribution, I think, started as a fitting function, right? And after you had this fitting function, and like you had to basically develop quantum mechanics to interpret it. So that's an example where in one limit it's initially it's a fitting function, and then it leads to a deep theoretical interpretation. So I guess to go to Chirag's example, you fit a galactic halo with a function, and then you realize I can develop a whole theory of violent relaxation that predicts for initial conditions why it will have a certain outcome. And so there's, I think, kind of these, there's a deeper level that we ultimately want to get at.
So to complement that discussion, I just had an idea right now that maybe the deeper level of understanding is when you, as a physicist, can address the question at the level of how many piano tuners are in Manhattan, right? So because then what are you asked to do? You're asked to apply general principles, right? That have that there's nothing specific there. It's just general principles that you know work, right? And so and then you get the dynamic, right? You have no idea how to calculate it. You get the dynamic, and then maybe okay, you need one observation to get to a guesstimated answer. But that, I think, is what entails understanding, whereas interpretability would mean at the level of the the fitting function or even the equation that governs that class of fitting of function fits.
Kind of on this comment, then I have a general question for kind of cosmology as a field, in that we emphasize this simplicity, but what if the true underlying phenomenon is beyond a simple one-page equation description? So, for example, I'm thinking like in biological science, a lot of human vision, right? Could we ever come up with a couple of equations that make you understand human vision? I don't think so. So, do we give up on those problems, or what do we need for those problems to be interpretable? What are we looking for? Suppose we're trying to solve a problem like this. What should we be looking for? What should we require from a paper that claims to solve such a problem, and so on? I think that's something that's very interesting to think about. In some cases, there's not going to be a simple equation, and what level of trust and verification, maybe these kind of things, should we try to look in that case?
Oh, I think about the mathematician, I think I have a different view. I think the kind of interpretability is not necessary to be equations. As long as we can reason with some language, that's fine. So for example, like for the machine, we might not be able, I think, finally to write down some equation governing neural network. It's already an equations, right? But perhaps we should finally be able to kind of tell which part, the function of which part is what, and in what condition it can work well, in what condition it does not work well. So especially the second part, like what's provided by the adversarial examples, I think those really help a lot about understanding the behavior of neural network. And about the level of interpretability, I think actually for low dimension is fine. So for example, if you have a banana likelihood and you want to use some likelihood-free method to do it, to fit it, I think that's fine. You really don't need so much interpretability. But it might be a bit dangerous when you go to higher dimensions still, because of the problem that, I mean, with limited number of simulations, we have kind of the limited information, right? Coming from the sampling, limit sampling. So there are intrinsic error of our knowledge. So I mean, I think sometimes we really need to think why we expect using a limit set we can increase, like especially for the acceleration of simulations, we train the network based on limited simulations, and then we expect we can scale it up to 1 million simulations and for some inference. But how the accuracy is all just built based on the 1,000 simulation. So then what we gain from this?
I think this is a really good point. I mean, one of the things I guess that I'm wondering about here is also, I mean, as long as I can quantify, like in this example, for example, like how many simulations do I need to get, or do I need at least to get confidence levels, accurate confidence levels, or you know, as long as I have some proven guarantees, maybe I'm happy enough. You know, as long as there's enough theory behind it. And I guess that's not exactly interpretability. Like as long as I can tell, like there's this and this guarantee that I will reach at least this accuracy with this in this method, maybe I'm happy with it. Or if I can, you know, get the epistemic and aleatoric uncertainty of my model fine enough to get like the error bars correct. Maybe in certain instances, when I, for example, only care about constraining certain parameters in a physical model that I already know, maybe I'm happy with that, you know, and I just have like a really messy data set that has maybe a lot of physics that I'm not interested in. I just need to extract something out of it, and I use a neural network for it, and I can quantify all of the uncertainties in it. Maybe I'm okay with just getting an answer for this parameter from this network. Like gas physics, for example, in cosmology would be, for us cosmologists, would be, I guess, an example for this. Any opinions? Yeah, again.
About this, still about like the speed up. I think I perhaps I just repeat myself again. Kind of, I don't believe neural network can do kind of magic or miracle things. We shouldn't expect that. It's kind of that because that will be very dangerous. Actually, like for example, when you have a chance to really speed up some algorithm, that's because there should be a reason behind it. There's some simplicity of this particular question itself. Again, the example is fast Fourier transform. That's because Fourier transform is not just a random transform. It's some particularly simple transform. That's why you can make it log and log n. So I think again, neural network might help us to find some simplicity in some kind of data, especially like field or high dimensional things. But really, the interpretability is about us understanding what is the simplicity, why neural network match some of the particular data. I think without this, we will tend to think it's a magic or miracle. But with this kind of interpretability, that will make it much safer.
Yeah, so I guess the point is, want to bounce back on what you said. You mentioned also HMC earlier. And we have some guarantees for HMC is that asymptotically, if we spend infinite computational power, it gives the right thing. But no one ever checks, spectral gap to see how fast it will converge or attempts any of this. We just hope that after we run out of patience, it gives approximately good results. And I think the notion of how much guarantees we need to satisfy ourselves is very dependent. To kind of address more of Siha's point, the problem, in my opinion, is that there's a huge gap between what we can understand, what is simple, and what is complex. Think about natural images. Can you write down a mathematical description of mathematical images that tells them that you're simple? No. Are like natural images random? No. They're somewhere in the middle. They're pretty simple on the scale of random to very structured, but we have no way of writing down any reasonable mathematical description of natural images. And I'm worried that as we progress towards more and more complex problems, that we solve the linear Gaussian part where we can easily write down the equation. That's done. We're happy with those models. They work well in some cases. We're now progressing towards stages where maybe, we're at the fifth or sixth order polynomial where there's no closed form solution anymore. And there's no reason necessary to believe that what we can understand in terms of equations matches the simplicity of what happens in nature. And with a flexible network, maybe it can exploit some of that simplicity despite us not being able to write it down explicitly.
I think a good example for this is what I call here machine learning priors. Where, for example, when we do image reconstruction, right? If you assume a Gaussian prior, it's suboptimal because the pixels are not Gaussian distributed. But you can learn a prior from the images with your machine learning model, and then you still have, your forward model and your likelihood to take care of like this is just your prior, this is just your pre-knowledge. So in a sense, I think, like for these kind of applications, I think we don't, my personal opinion is that we don't have to interpret what the machine learning model does to learn the prior, as long as it helps us solve this problem. One final remark, maybe 2 more minutes, 2 more final remarks. Yeah. Oh.
This is something we sort of touched on loosely, but I think in the broader astrophysics community, interpretability and sort of trust are used interchangeably, and I think, if they are different questions, but to some extent, if I develop some method, and even if I've tested it on a huge suite of simulations, if I then apply it to, I don't know, boss data and discover something new and surprising, would even I believe it if it was a completely, opaque system to me, even if you've tested it very thoroughly on your simulations? Interpretability often gives us some more confidence in things, I think.
Just to address this, I believe it's something akin to the prior of Bayesian statistics, right? You basically, you can put anything you want into the prior, including the level of your belief in something, right? And if you trust something, you would put a prior that is very, very close to what you believe will be, right? And so on and so forth. So it's really, in a sense, it's coming full circle to eye of the beholder, or what feels good, what gives us a feel good feeling, right? I don't know.
I think that was a good final conclusion. Whatever makes us feel good. And yeah, with this so thanks the audience for your participation, and applaud yourself.
The actual organizers.
Thank you to everyone for coming to the first in-person cosmology cross machine learning workshop after post-pandemic. No, I don't think post one. And so thanks to the speakers for the great talks. Thanks to the chairs for the great discussion. We hope that you got some inspiration for new project, and tomorrow we will have this hack day, so we hope you can collaborate each other or create a new project, new interaction. Thanks Shirley, David, and Flatiron for hosting the workshop, and thanks to Melanie and Comfort Hand for helping us. I don't know where are they, so thank you.
And someone lost something, please go down to the lobby to check with security. Another thing, if you want to stay tomorrow and don't expect free lunch hanging in here, you should let us know, and then we can get your stimulus account so you can order lunch. Yep, I think we have covered all bases. All right, thank you everyone. Drinks upstairs.